Number 1. This is like the your turn that we did in class. So the point of this problem is to realize that whether you're in fresh water or in salt water, the ship is floating. So when you're floating, doesn't matter what kind of liquid that you're in, you're going to have a buoyant force and you're going to have a weight, and they will be equal to each other because when you're floating, you're in equilibrium. So in both cases, the buoyant force is equal to the weight, so that means that the buoyant force is the same whether you're in the fresh water or the salt water. So you can say the buoyant force in the fresh water is equal to the buoyant force in the salt water. So rho of the fresh water times the volume of fluid displaced, the fresh water times G equals rho of the salt water times the volume of the fluid displaced in the salt water times G. So the G's cancel out. And then since the density of salt water is greater than the density of fresh water, since this here is greater than this one, for the two buoyant forces to equal each other, that means that the volume of fluid displaced in the salt water must be less than the fluid displaced in the fresh water, which must be more. So that's why the answer is less. Number 2, aluminum and lead are at the bottom of a lake. So which one has the greater buoyant force on it? Well, the mass is the same, but density, which is equal to mass times mass divided by volume, tells us that the volume is equal to mass divided by density. So whichever one is less dense will have a greater volume. Aluminum is less dense than lead, so aluminum will have a greater volume. So the buoyant force will be greater on aluminum because the buoyant force depends on how much liquid is displaced. When you have both of them in water, the aluminum, and I'm not drawing these to scale, but the aluminum will be bigger than the lead, so it will displace more water. That means it will have more buoyant force on it. Number 3, this is just Pascal's principle, just a definition. And number 4. So the submarine is on the bottom of the sea. And we want to know what's the normal force. Well, if it's on the bottom, that means there's a normal force here. Since it's in the water, there's also a buoyant force. And there's also a weight. So it's sitting there, it's in equilibrium, the sum of the forces equals 0. So the normal force plus the buoyant force minus the weight equals 0. So solve for the normal force, we'll get the weight minus the buoyant force, which is what this says, the weight of the sub minus the weight of the displaced water. By definition, the buoyant force is equal to the weight of the fluid displaced, which is what this is saying right here.